Hello, everybody. My name is Eduardo Gonzalez. I work right here at the Denver Museum of Nature and Science. Thank you for joining us for another episode of the Science Division Live. Today, we have James Hagedorn. He is the geology curator here. He's an expert on rocks, fossils, and minerals, all around a rock star. He is from the University of Southern California, and today he will be talking about ancient sandstones. Stay tuned as James will answer all your questions at the end of the presentation. It should be right here.
Excellent. Thank you so much, Eduardo. Thanks everyone for tuning in. This is going to be fun. You know, one of the things that's great about being a geologist is that we get to surf not only on the earth today, but we get to surf rocks in deep time, including on some pretty amazing ancient beaches. Hey, I'm going to share my screen with you all right now because I want to show you some pictures of some rocks, some fossils, some minerals, and take you on a journey, or maybe really give you a progress report of a project that we've been working on for the last couple of years, and hopefully involve you in that journey. Give me just a sec. All right, so here we are on top of Liberty Point in southern Colorado. And for those of you that have been to this 9/11 memorial, most of you probably hung out on the top of the cliff here. Well, if you were there and you looked over the edge, you might have seen a geologist poking around down on the bottom because this cliff is made up of amazing layered sedimentary rocks. And the middle band of these layered sedimentary rocks that we're seeing in this cliff here is a rock unit called the Codel Sandstone. It's named after Codel, Kansas, a small town that I'll show you in a bit. And I've been to this point many times for the great views, but today I want to talk about this rock unit that makes up the most of this cliff here, because this rock unit is exposed here in Colorado, it's exposed in Wyoming, in Kansas, in Nebraska, and other places. And it turns out that it's a rock unit that is kind of an enigma, but is also pretty important. And using modern techniques, we and colleagues around the area here have been able to go back to these rocks to kind of tease out some of their secrets. And so today I just want to give you a progress report on that. So here's me out in Kansas at King Hill, and I'm standing next to a nodding donkey. That's why they're called that. They're also known as pump jacks. And this is a kind of clunky device that's used to extract oil and gas, mostly oil from the ground. And the Codel is a relevant rock unit to many of us because in between the little particles of sand are lots of pore spaces that house important liquids that we care about or that we use. And in this case, this is oil and gas. But you know, elsewhere in Nebraska and even in Kansas, this rock unit actually houses liquids that are used as groundwater for drinking water, for agriculture, for people, and the other things. And so the Codel Kansas, the Codel Sandstone is actually a pretty useful rock. The other reason the Codel Sandstones is useful is because it tells a part of the story of the bathing of the belly of the mid-continent of the United States and Canada with this giant ancient seaway, which you can see this paleo satellite image of on the left here. And this is a interior seaway called the Western Interior Seaway that slooshed across the belly of North America for millions of years. And this is a reconstruction from about 90 million years ago. And lots of the fossils and rocks and minerals and deposits in Colorado and the American West and beyond were laid down layer by layer in this seaway, either as muds that settled out of the water, or that rocks full of pebbles that came off of deltas, or as set shells and lime particles that built up limestones beneath it. And these layered rocks, some of which you saw in the picture earlier, geologists kind of read like a barcode or a UPC code at the grocery store. And this crazy diagram on the right-hand side of your screen right here is an illustration of one of these. And you don't need to worry about all the names on here, but the layers on here, the yellow layers are sandstones. The gray layers are mudstones that become shales, rocks made out of mud. The ones with the little brick patterns are made out of shells and other materials. And so we have, over the generations, begun to understand the record of Earth history that was deposited by this seaway, but there's some gaps in our knowledge. And one of the biggest gaps is right here, surrounded by white in the right-hand side of this diagram. And that gap is a gap that surrounds the rock unit, the Codel Sandstone. And so, fortunately, the rocks are still here. After all, they've been here a long period of time. And today I want to take you on a journey to illustrate how we're learning more about these rocks, about how they were deposited, where they were deposited, and when they were deposited, where did all the sand come from? And what does it tell us about this sort of gap in knowledge of our understanding of this ancient seaway? So the Codel is exposed all over. Oftentimes we go out to an outcrop like this. This is the type section at Codel, Kansas. And we look at the mudstones beneath it on the left, or we look at the limestones on the right, or we look at the sandstone pile in the middle where two of my colleagues are standing here. And we go out to these rocks and we measure them and we separate out the grains of sand, or we look for structures in them. And you know, one of the questions that people often ask me is like, James, these rocks have been here for 100 million years. Don't we know everything about them already? Why are you going back? Didn't the old geologists look at them? And well, the answer is they sure did. But we have new techniques that can analyze these rocks or tell us things about them that we couldn't even dream were possible back in the day. Think about your iPhone. Your iPhone is more powerful than your desktop computer was a decade ago. Heck, probably 5 years ago. So just as an illustration, we go out there with techniques, we measure these rocks, we look at fossils and structures in them, and we create a diagram like the one over on the one on the right. And this diagram is kind of like a stacked column or artistic representation of the rocks that you see, kinds of rocks that you see at the left. Well, here's an example from 60 years ago. Here's an example of the same area from 30 years after that. You notice that it's getting a little bit better and a little bit more detailed. And then finally on the left, here's our measured section or sort of description of these rocks from just last year. And so with every generation of geologists, we're standing on the shoulders of our predecessors, using new techniques, adding to our understanding of these rocks. And I want to present some of that data here because it's how we understand, how did you build up this pile of sandstone? Was it an ancient beach? Was it deposited at the bottom of the sea? Or was it something else? So we look at rocks in the field, and these are all little pencils for scale. People always ask me why I'm taking pictures of my pencil or my rock hammer. Well, it's a scale, so you know how big the thing is that's in the picture. And so we look at structures in these rocks and try to decipher what they are. And to be honest, the Codel doesn't have a lot of useful structures in it. It's oftentimes kind of blah looking. My neighbor once said that all rocks are either tan, red, or brown, and well, she's not far off. So anyways, but sometimes you find interesting things in them. So here's a shark's tooth from the Codel, a couple of vertebrae from other fish and sharks that swam around in the seas above this. And on the right here, next to the pencil on the right, is a very long vertical burrow made by little shrimp-like creatures that burrowed in the sand. And so we can use clues like fossils or structures that we see in the rocks to understand how these rocks were deposited. In this case, they were broadly deposited in a marine setting, not unlike the Seaway I showed you that picture before. What's really cool is that we've been looking at these rocks carefully along with other geologists, and you can see structures of individual moments in time every now and then. And here's an example below the hammer right here. On the bottom of this slide, you can see this swaley or kind of undulating bed that my mouse is moving across here, where the layers go up and then down and then up again. And that's called swaley cross stratification or hummocky cross stratification. And it's produced as storms agitate or disrupt the bottom. So isn't that cool? We can see a storm at a moment in time, 90 million years ago. So we've been putting together this kind of information to understand this system a little bit better based on outcrops, but we've also been looking at core. And this is an illustration of a core of rock that's been stacked in boxes and then cut in half so we can see the insides of it, with the older part of the core over on the right and the younger part of the core on the left. And you could just look at the colors in here and say, wow, the core on the right over here, that rock's kind of gray and black. It doesn't have a lot of layering in it. The core on the left has a lot of layering in it and is kind of striped, and the stuff in the middle is kind of all jumbled apart, right? And that's exactly what you see in the outcrop, except in a core, you sometimes see it better because you can cut it and wet it and look at it really closely. In this case, right beneath this hole here, which was drilled out to sample the geology and the minerals, you can actually see where a burrow on the bottom right has disrupted a layer of mud that was once sitting on the seafloor. Who knows, maybe that was an ancient shrimp or snail cruising across the seafloor back in the day, 90 million years ago. So we can assemble this kind of information and get a sense for what the environments were like that might have produced the Codel. But to really sink our teeth into it, we need to get microscopic. And we need to know, what do these sands look like under a microscope? Bada boom. Thanks, Benita. That's what sand looks like under a microscope. What the geologists really do is we don't actually break apart the sand, but we slice it into little things called thin sections that we shine light through and then examine under the microscope. And these are what are called photomicrographs here. We've got a team of people here that uses these at the museum and elsewhere to understand what the grains of quartz sand that actually make up the rock look like. And you can tell a lot about a rock and environment from individual grains of sand. And so the fancy colors on here, don't worry about those, but the kind of whitish looking blobs in here are quartz grains. Those are sand grains. And the bottom of the Codel sandstone is roughly over on the left at about 1-ish meters. And the top of the Codel is down on the bottom right. These are samples from different parts of the rock unit. And the general trend you might be able to see from this slide alone is that the grains of sand are bigger as you go from the bottom of the Codel to the top. You might also notice that these sand grains, most of them aren't round in cross section. Most of them are kind of jagged and angular. And that means that these grains of sands haven't been bashed against one another very much or rubbed a lot in streams and things like that to get worn down. So they're pretty young grains. You might also notice that there's some kind of really long jagged blade-like things. And there's one in the bottom right image here that kind of looks like it has hairs on it. And that's actually a piece of a fossil tooth. So we can learn a lot about the Codel from that. We've looked at a lot of these samples under the microscope. And one of the things that we found is that there's actually some really unusual populations of grains in these that are rather abundant. Two of these are illustrated on the left here with a black arrow. These are what are called zircon crystals. And zircons are kind of nature's versions of almost a diamond. They're crystals that are pretty darn hard that get ejected from volcanic eruptions and fall into the sea or get deposited in ash like Mount St. Helens or Mount Pinatubo. And the Codel is actually smack dab full of these things, which is unusual. And these are illustrated at left with these little black arrows. The other thing is there's lots of grains of chert. There's one illustrated at right here at the end of this white arrow. And chert is really interesting because chert is basically what glass is made out of. And it can form in a lot of different settings from granites to other places. But it's a pretty hard mineral too. Basically, it's quartz of a special type. And the Codel is just absolutely full of it. And we were kind of scratching our heads wondering, well, why does the Codel have so much of this stuff? And some samples have a lot, some samples don't have very much. And what we really thought we might try to do is to kind of find, well, what's the source for these grains? What's the source for these volcanic grains or these other glassy-like grains? And so we went up to Wyoming, and here's a colleague, Lynn, sitting on an outcrop. And one of the things you might notice about this outcrop is there's a lot of gravel below her feet here. And I'll show you a close-up of that outcrop in a second, because that outcrop is actually full of gravelly kind of cobbles and particles. And many of these cobbles and particles are chert grains, except they're big, they're pebbles, like they were washed in from a stream or a delta or something like that. And one of the things, the rocks that she's sitting on or that are in this picture are the temporal equivalent of the Codel Sandstone in Colorado and Kansas. They're just up north a bit. And so we wondered, gosh, could this possibly be the source for the chert in the Codel? And so Mark Longman and other people, Rich Botchers, have been thinking about this for a while and put together a bunch of diagrams. This is just one example of it, but you can kind of think of the stippled area in these columns on the bottom here, this kind of dotted area on the bottom of the yellow column is representing the abundance of chert in samples that are kind of near Wyoming, and the ones over on the right, samples that are kind of far away from Wyoming, down towards New Mexico and Kansas. And one of the things we noted is that the abundance of chert in the sandstone decreases as you go from Wyoming down south and to the southeast. Similarly, the size of grains decreases from big cobbles like you see on the left here, to tiny little sand grains smaller than the period at the end of the sentence in today's newspaper. The other thing that we can do in these rocks that we've been doing is integrating data from the community about ancient current indicators. And so in rocks, one of the clues you can look at is the orientation of the bedding. In this case, the bedding below the hammer here is kind of tilted. It's tilted down towards the right side of your screen. And that tilting, along with other structures like ripples and channels, lets us know that the current, in this case, was moving roughly from the left of your screen to the right of your screen. And we can make notations like that at different outcrops. Lots of folks have done this. And that data we plot on these funny looking diagrams on the right, which is like looking down at a compass. And you can think of the yellow petals, the yellow lines on here as kind of like arrows. They indicate the direction and the amount of currents, ancient currents, that we were able to measure in the Codel Sandstone. And the end of the sort of summary of this slide here is that most of those currents on this diagram, about 3/4 of them, are pointing south, which means that at least in this part of Colorado, sort of north of Denver and south of Denver, that most of the ancient currents that were moving these sand grains, and zircon grains, and quartz grains around in the Codel were going from north to south. Well, that's good, because that's kind of where we think one of the big sources of the cherts might be, those big pebbles that I showed you earlier. And so our team has been trying to puzzle over this, and we've been putting together working hypotheses. And this is just an example of one of these sort of pictorial or graphical hypotheses about what Colorado and vicinity, Colorado's right here in the middle, might have looked like during deposition of the Codel. And these purple arrows indicate the direction of current flow that was indicated potentially by some of those structures I just showed you a minute ago. And so the great thing about this, putting together a diagram like this, it sort of pieces it all together and says, well, maybe you got some volcanoes up here that are spewing out zircons and other stuff, and it's making its way into the Seaway and oozing on down south. But, you know, when you make a hypothesis as a scientist, you know from the minute you make it that you're wrong. That's right. Science is the process of being wrong, of making mistakes, and then learning from them or correcting those or testing them and moving forward closer to the truth, right? So this is a testable hypothesis, and our team's in the process, along with others, of trying to test this and see if this is a good explanatory diagram to account for how the Codel and some of its compatriots were deposited. And one of the great things about working in the American West here is not only do we have awesome outcrops and fantastic mountains, but we have core. We've got cores. Some of these are indicated at the right over here is a picture of a couple cores. There's hundreds of cores that perforate the rocks below our feet and allow us to read that ancient barcode. Except in addition to that, there's another kind of barcode we can read. And that is that when wells are drilled, they also collect sort of electronic information about the characteristics of the rocks. And they plot this electronic or geophysical information on diagrams just like this one over here. And there's a whole team of folks here in the Metro Denver area and the American West that know how to read this subsurface information from the thousands and thousands of well logs, and that are putting it together to better understand the overall distribution of the Codel Sandstone and how it was deposited. And one of the things that we learned, or I should say we relearned this last year, was that there are actually 2 Codel sandstones and maybe more. The diagram at the left, the yellow, the tan, the gray, and the blue, and the red indicate where the Codel is in southern Colorado and western Kansas. This area up at the top here indicates where it is in northern Colorado, Wyoming, and into Nebraska. And the colors represent thicker Codel in red, thinner Codel in gray. These other pink and green things are kind of other rocks of other ages that are nearby. Denver's here in the black box. Gosh, I never thought of Denver as a black box before, but maybe it is. But the thing that really startled us is that indeed in the middle of the state right here, what's called the no COZO or the no Codel zone, there's no Codel. And so we're really a little bit flummoxed by this, because how do you explain the deposition of this rock unit with a giant gap in the middle? It's like not having all of the story there. And so is it possible that there are 2 different settings that produce the Codel, or that the Codel was deposited in 2 different places by the same environment, but at different times? And so to figure this out, we've gone back to the field, and we've gone back to cores, back to well logs. And I just want to give you an example right here. Here's a picture of the Codel at the top of this image here. I showed you this earlier. See how thick the Codel is? It's, you know, maybe 30 feet, right? If you go 2 miles away, you can go up onto a hill, and the Codel is the bottom of the slide at the lower left. It's about 10 feet. And then you go about 5 miles away from that, and the Codel disappears to only a few feet. And so we can see that the Codel is disappearing spatially in the basin. And one of the questions is, was the Codel originally deposited as a giant layer of sandy frosting on the bottom of the seafloor, and then later on some erosional process scooped out or removed parts of it? Or maybe alternately, another hypothesis is maybe there was some kind of a topography on the seafloor with a deeper spot over here and a shallower spot over here, and the Codel just sort of filled in and is thinner where there was a paleo high or an ancient high, and thicker where there was an ancient low and more space to pile up sand. Well, all of those are valid hypotheses. We're thinking about testing them, and one of the best ways to test them is by dating the rocks so we know we're not comparing apples to oranges. And so here's me going, holy guacamole, look at that detonite. And this is from up near Kremlin, Colorado. And a bentonite, if you're wondering, is basically a fossilized ash. And it's kind of grotty looking. You kind of got to dig it out with a spade. It feels like Play-Doh. But ashes are really special because you can get an age on the rock with great precision by dating the crystals in them. And so we've been starting to do that with a bunch of collaborators from the US and Canada. And this is, again, that crazy barcode I showed you earlier on the right, where we have this big gap in time illustrated by this white band with a Codel sitting smack in the middle of it. So we've been going out and dating these ashes. Their preliminary data is from all of these red stars. And these are the ages in millions of years. And so I don't expect you to kind of immediately digest all these numbers, but the take-home story is twofold. One, all the ages up at the top are older than the ones on the bottom, and they're all in sync with one another, which is great because it means that all of our measurements are congruous and acceptable and meet multiple tests. And the other thing it means is that the Codel right in here was probably, which we bracketed with ashes now, was only deposited in a few 100,000 years. I know that sounds like a long time for us, but for a geologist, that's like nothing. And the gaps surrounding it were at least 1 million years or 2 million years each. So anyways, that's some preliminary data, waiting for more of it to roll in from various labs. And I'm looking forward to getting out on an outcrop with you or maybe some of our community scientists and other partner colleagues illustrated here to do that. And I just want to end by thanking all the people that have fed into this research. Although I'm here on the screen, this has really been a team effort, and we could not have done it without everybody's help. So we're very grateful for that, and thanks.
Thank you, James. I personally got one fast question. I never thought I would ask this, but how do you date the rocks?
Well, this is a little bit different than online dating, but the short version is that those little zircon crystals I showed you earlier are basically like kind of like a clock in like an hourglass. They're really hard. If you've heard of the gem cubic zirconia, right? That's sort of a version of nature's own zircon. It's a really hard crystal, and zircon has it has a couple of ingredients in it, namely uranium, that decays into lead. And kind of like an hourglass, when you flip it upside down, you can count the rate at which the sand grains drop from the top of the hourglass to the bottom. Well, geologists and geochronologists can date the rate at which uranium decays and to lead. And because we know the rate at which that happens, we can count the ratio of the original stuff, the parent, to the end product, the bottom or the daughter, and come up with a number. And because we're detectives in deep time, and any good detective doesn't use just one clue, when we actually date the rocks, we use 2 or 3 different clocks. So we use 2 different uranium systems, and then we also use fossils to check it. So that's a great question.
I'm assuming this is one of the newer tools they've been getting used. What are some
Yeah, well, uranium lead dating has actually been around for quite a long time, but the accuracy has jumped orders of magnitude. So for example, those dates I showed you, to go back to a rock that's 100 million years old and be able to say plus or minus 10,000 years how old it is, that's like, think about the percentage. That's incredible precision, right? And accuracy. And when we were able to use uranium lead dating 20 or 30 years ago, the error bars were, hey, that's plus or minus 5 or 10%, right? So, we're getting down into the thousandth of a percent in some cases, right?
Wow.
So it's fantastic. I mean, it's technology and also people's determination to improve the science is really what's propelled us here, as well as the ability to communicate science, right?
And then the other way you were talking about is connecting with fossils, correct?
Yeah. So fossils are really a key part of the story too, because fossils can tell you the relative age of things, because, for example, fossils are constantly evolving and going, or organisms are constantly evolving and then going extinct. And so, for example, dinosaurs died 65 million years ago, right? And trilobites died about 250 million years ago. I mean, not died, but went extinct. They disappeared. So if I find a rock with a trilobite, I know it has to be older than 250 million years. And if I find a rock with a dinosaur in it, I know it's kind of younger than the trilobite, but definitely older than 65 million. And then if I find like a really happy mammal with a power bar, I know that it's got to be younger than that, right? And so, we can use that relative dating to kind of figure out the age. And of course, I'm using kind of crazy examples, but people have gone in the Cretaceous, they use this things called ammonites. And ammonites are these big coiled squid-like shells that, they sit out and they kind of propel in the seas. And there are millions and millions of these in these rocks. And they evolved, and people have learned how to sort of read the ammonites, if you will, to know which ammonite is from which zone, right? And they've been able to put together a succession that's at a resolution of about 100,000 years.
Wow.
Right.
And does Colorado have any sandstone deposits that are have a lot of megafauna fossils?
We do. I mean, we have got sandstone deposits that have mammoths in them that are pretty young. We've got sandstone deposits that have petrified trees in them. And we've got sandstone deposits that have huge dinosaur trackways in them. Yeah, so Colorado's got a lot of great sandstones with cool fossils in them. And actually, if you go up to Kremling, Colorado, there's actually a special fossil preserve up there that has some of those giant ammonites in it. I mean, get on my screen here. They're like this big.
Wow.
Yeah. So, they're out there. I mean, you're not allowed to collect them, but you could go look at them, and they're really amazing.
Yeah, we're not encouraging collections here. Well, I'm gonna check the comments. I want to make sure that I have not missed any questions. I think we're good. I have a comment from Chris talking about the 9/11 memorial, saying that there's something cool about this place, by Chris Jones.
Yeah.
And Melissa talking about how this brings her back to college mineralogy days.
Nice. Yeah. Well, I always tell people I'm a detective in deep time, right? And people want to know, well, are you a geologist, or are you a paleontologist, or are you a mineralogist? And I kind of say, I'm kind of a general scientist in deep time, because it's okay to use minerals or chemistry or fossils or structures or bedding to kind of figure out what happened at the crime scene. And, every crime scene is different. And, one of the great things about science is that it is an investigation, and you can pull in colleagues, whether they be community scientists from a museum, or a professor from a university, or someone in Saskatchewan who's the Jedi master of ammonites, and you can collaborate, and the internet allows us to do that much more easily, and you can work together to kind of better understand that crime scene. And in our case, this is not a crime scene, but it's a rock unit that's relevant, that's economically useful, and that we don't understand that well, and so it's kind of fun and it's right in our backyard, so it's kind of fun to do that.
Yeah, I've explored a little bit around in Colorado, but I have a question for you. What is the most memorable fossil you found in your explorations around here in Colorado as you're doing all this research?
Oh my
God.
God.
I know it's a big question, but I'm curious.
Whoa, what is the most memorable fossil I found in Colorado? Okay, first I gotta give props to Bob Reynolds, Tyler Leeson, and Ian Miller, who showed me this, and I didn't believe it at first, but down in Colorado Springs, there's a rock unit that it's actually a sandstone, and in it is a fossilized tree stump, right? And this thing is big. Okay, by the way, this is my actual living room, not a virtual living room, but it is about the size, or maybe bigger than my living room here. It's huge. The stump is, as big around as a gigantic, coffee table or something. And what's interesting about that is not only that it's beautiful, it's kind of weathered out on a hillside, so you can kind of look up and see it, and it calls to you in the way as a redwood. But that fossilized tree is preserved as the mineral dolomite, right? And I had never seen a tree preserved as the mineral dolomite. People are like, what the heck is dolomite? Well, dolomite is kind of like a modified version of the same mineral that most clams make their shells out of, right? Which is calcite. And it has a couple things, different ingredients and shape of the crystal structure. But at the end of the day, it is not what a tree is made of, right? And so that tree, which was originally, woody tissue, got replaced by this other weird mineral in a sandstone deposit. And I don't know that anybody has figured out how that happened, but it is one of the weirdest fossils I've ever seen, and it's right in our backyard. And someone's going to figure that out, and it'll be another detective story for someone to figure out. And that's a deposit that's also economically useful. So who knows? Maybe it's linked.
Another one of the crime scenes.
Exactly.
Well, thank you so much. I want to make sure that we got all the questions answered, all the comments done. Thank you so much for joining us, James. I'm here to just, if you want to see more of the videos with James in them, you can check out our YouTube channel. We have all the videos there. He's an amazing guy. You can come to the museum whenever you want. We're open every day. And if you can come visit us at our website at dmns.org. Thank you so much for everything. Thank you, James.
Thanks, Eduardo. Thanks, Tim. Thanks, everyone, for tuning in. Have a great day.
Thank you so much. See you later.